Today, Chris and I are going to talk about the static detection of backdoors, and we'll be talking about doing that in both source code and binary methods. I'm Chris Weisopel, CTO and co-founder of Veracode. Veracode is a static binary analysis company. Previously I was at Symantec, at Stake, and way back in the day at Loft. And you may know me from such famous tools as LoftCrack and Netcat for Windows, which I've been told it has been used as a system backdoor, but I'm not positive. I'll let Chris introduce himself.
Hi, I'm Chris Eng, Director of Security Research at Veracode. Previously also been with Symantec and at Stake. Before that, the Department of Defense for a little bit. I worked on the less popular than LoftCrack at Stake web proxy tool, which if you were doing web pen testing 5 or 6 years ago, you may be familiar with. So this is a quick overview of our talk. Let's go through background about backdoors, talk about some different backdoor mechanisms that we've grouped them into after doing a survey of the past 20 or so years of backdoors. Talk about some additional detection techniques around those. Talk about the idea of malicious code and other vulnerabilities as potential backdoors, and then conclude, take some questions at the end. Just a little pop culture here.
Yeah, I think probably everyone has seen War Games, but you might not remember the scene that we're going to play that well. And War Games kind of introduced the idea of the smart aleck high school kid as a hacker to American culture, and kind of started that imagery in the early 80s. And it also introduced the concept of the backdoor to popular culture, which I think before that was probably a pretty obscure notion, and backdoors plays a key role in the movie War Games. So this is our entertainment.
Can you wait here?
Why?
Because these guys can get a little nervous. Jim.
Oh, Lightman.
Hi, Lightman.
I want you to take a look at this.
Hey, what's that?
I wanted Jim to see that.
Wow, where'd you get this?
I was trying to break into Protovision. I wanted to see the program for their new games.
Hey, wait, Jim, I'm not through yet.
Remember you told me to tell you when you were acting rudely and insensitively? Remember that? You're doing it right now. Theater-wide biotoxic and chemical warfare. This didn't come from Protovision.
You bet it didn't. Ask him where it did come from, Jim. Go ahead, ask him.
I told you already.
Looks military to me. Definitely military. Probably classified, too.
Yeah, but if it's military, why does it have games like checkers and backgammon?
Maybe because those are games that teach basic strategy.
Jim, how do I get into that system? I want to play those games.
You're not supposed to see any of that stuff. That system probably contains the new data encryption algorithm. You'll never get in there.
Hey, I don't believe that any system is totally secure. I bet you Jim could get in.
Yeah, I bet you couldn't.
I bet you he could.
Well, you'll never get in through the frontline security, but you might look for a back door.
I can't believe it, Jim. That girl's standing over there listening, and you're telling her about our back doors?
Mr. Potato Head. Mr. Potato Head, back doors are not secrets.
Yeah, but Jim, you're giving away all our best tricks.
They're not tricks.
What's back door?
Well, whenever I design a system, I always put in a simple password that only I know about. That way, whenever I want to get back in, I can bypass whatever security they've added on. That's basically what it is.
Yeah?
Okay, you really want to get in, find out as much as you can about the guy who designed the system.
Oh, come on. I don't even know the guy's name.
Where are you guys dumb? You guys are so dumb. I got this thing all figured out. I figured it out all by myself.
Oh, yeah, Melvin? How would you do it?
The first game on the list. Go right through Falcon's Maze.
So I guess Jim here is a programmer. He's programming classified systems, and he's putting backdoors in. So I wonder how many programmers have thought of that over the years. So let me just go through the major categories of backdoors just to frame what we're going to talk about. There's a category backdoor called a crypto backdoor, which is a designed weakness in a crypto algorithm. So whoever implements this algorithm, there's some sort of certain keys can be weak, or you can be able to perhaps break the algorithm quicker. And it's something that we're not going to talk about, but I just wanted to have it in there for completeness. System backdoors are probably the most popular reference when people talk about backdoors is talk about backdooring an entire computer system, and that's typically done with a piece of malware or a rootkit, where essentially if you get that piece of software on the system, it's not supposed to be there essentially, and you're backdooring the entire system. What we're going to talk about today is application backdoors, which is something which is inserted by someone who has access to the source tree or a binary distribution point, and they're taking a piece of presumably legitimate software which a system administrator is going to install on their machine and thinks that everything's okay, and they're putting in something that's going to bypass the normal security mechanisms of that piece of software. Now, of course, this could result in a system compromise also, and you'll see that a lot of application backdoors do have command shell access where you can run arbitrary commands on the system, but it doesn't necessarily need to compromise the system. It could just access the data that application has access to. You could think of a backdoor in a database might just be able to access data in the database and not the entire system. And generally, we're going to give examples of PHP and C programs, show some code with backdoors, but any programming language could be used. So what are typical targets of backdoors? Web applications seems to be a pretty popular one. We have some examples. Web applications are running as a server. They have access to the network. Seems like a really nice thing to backdoor if you're looking for a way to get onto servers. Any kind of server application is generally pretty good. You want to if you're picking your backdoor target, you want something which is running all the time. Typically, something that has network access is better because it won't look like an anomaly for the software to be communicating over the network. Network appliances seem to be a popular place. It's not clear whether these are all intended to be put in by the manufacturer or not. It seems like for support purposes, they like to put a backdoor in. So if the user locks themselves out of the appliance, there's a way of still supporting that system. And we have some examples of those. And finally, operating system is probably the holy grail for someone who wants to put in a backdoor, because not only do you have administrative access, but it's very, very widely deployed. And there was a case where Linux was attempted to be backdoored, which we talk about. So there's a lot of motivation to put a backdoor in code if you have access to that source tree, because you're going to get your access to systems you wouldn't normally get access to, because maybe the system's very well maintained, has multiple layers of security, and it'd be hard to social engineer a particular system engineer to get something on there. But if they use a particular kind of software, and you can hit the distribution point, or it's open source, and do that, you have the administrator installing your access onto the system. Typically, when you have an application backdoor, you're using the normal networking traffic that the application would be using, so it doesn't show up to an IDS, because it just looks like the regular usage of the system. So that's another nice benefit of doing this. And I think part of the motivation is just, even if you don't attempt to be malicious, just like Jim in the movie, he just puts one in because he might someday want to get back in. and he has access, so he's going to go ahead and do it. So what we're going to talk about today is detecting backdoors through static detection. There are certain classes of backdoors which probably could be done with dynamic detection, but a lot of what backdoors are, it's hidden functionality, it's hidden code paths in the system that aren't typically exercised unless you already know they're there. So it's difficult to find them using dynamic analysis. Now, of course, this is going to be pretty imperfect. We can't determine what all application logic is going to be, but by layering a few different techniques together, hopefully we're going to be able to catch some of them. Another interesting thing we found from just surveying the different backdoors that have been discovered over the last 20 years is if there was a backdoor in a binary, something that was just distributed in binary form, it typically took years for that backdoor to be discovered. And if it was an open source program, some of the backdoors lasted for up to a few months, but most were detected within days. So you could see that if you're able to scan the source, or obviously you can just do human review of the source, it's much easier to detect them. And I don't think a lot of people, when they audit code for vulnerabilities, are necessarily looking for backdoors. So this is these are some of the rules we have for looking for them can be added to a normal security audit. So our first category is special credentials, which is probably the most popular and simplest kind of backdoor. This is like what Jim talks about in war games. He just puts in his own special username and password. But it could also be a password hash. It could be a key. Essentially what it is it's something that's hard-coded into the application that will bypass the normal password table or keys. So the first, one of the first ones we found is Borland's Interbase in 2001 was discovered to have a backdoor in it. And this lasted in the code for 7 years when the program was distributed in binary form. It wasn't until it was open sourced that it was quickly found when someone started auditing the code. So the way this one worked is when the password database is created in the database for the first time, it inserts a hard-coded username politically and a hard-coded password correct into that password table. And so every instance of Borland Interbase 4, 5, and 6 would have this password that would work. It ended up being equivalent to administrative access on the system because you could write your own user-defined functions. So here is the code that actually put in the back door. So if you can see at the top here where we have locksmith user, what it's doing is it's creating a database record. It's copying the static value locksmith user into the record. Then it's coming down here and it's taking the static password, locksmith password, and it's doing a crypt on it, and it's copying that into the record, and then it's down the bottom here, it's inserting into the database. So you can see that, if you can find the code, this is going to be fairly easy to find because you can look for the crypt routines, and you can look for static values being encrypted. Now, if a static value is being encrypted, that's kind of suspicious, right? Like, why would you necessarily be doing that? So that is one of the techniques, and I'll go through the different detection techniques we came up with for this category. This was an appliance that had a special credential baked into it. This was found by Brian Hasek at Stake, and essentially what he did was he took the Intel NetStructure SSL accelerator, and he opened it up and took the code off of the hard disk and started auditing the binary. And he discovered that there was a code path in there where there was essentially a password was being computed from the MAC address, and that was being checked against also, as opposed to the normal password check. So the way it's designed to compute it off of the MAC address, it seems kind of suspicious that this is probably put in by the manufacturer on purpose for support reasons. The problem with this was anyone on the local network can read the MAC address and then compute the password. So it was essentially you got root privileges on an SSL accelerator. So on one interface you have the traffic in the clear. So it was a pretty nice box to be able to compromise. So Intel fixed this pretty quickly. Here's we don't know how long that one existed in there. It was probably in there for a few years though before it was discovered. This next one, Cart 32, was a Windows shopping cart, and I believe this one was found by David Litchfield. This one existed for over 5 years in the code, and again, it was binary, so you needed to do binary analysis to find this. And there was a baked-in special hard-coded password, Wemelo, and if you knew that, you could then execute some special commands on the system. And here's another sort of appliance here, the APC Smart Management Card. This one looks really suspicious as a manufacturer password, but they had a fixed password that you could use, and I guess this was discovered by dumping the device firmware. So all these things kind of have one thing in common. They're all using usernames or passwords or potentially password hashes. So one thing you can do is look for ASCII strings and look for comparisons against them, things that would be static values that could potentially be passwords, so they fit into that mold. Another technique is to look for hashes, and hashes are probably a particular length because they're probably using a common hash routine. So you can look for things of 128 bits or 160 bits, and then look for those static values, and then look for comparisons against those. So the automated approach can find these rather quickly, and then you manually can look through those. The other one, which would have found the Borland backdoor, is to look for. Oh no, this is the key one. So the other one is to look for things that are going into crypto functions. So find the crypto functions and look for static values going into those functions. Another thing that's kind of interesting to do is look for the randomness of static values, because you have a lot of static values that have high entropy. Those are potentially suspicious. Could be encrypted code or encrypted values that are stored in there, and it's just trying to be hidden from the auditor. So the next category is hidden functionality. And now they've got you all distracted. The hidden functionality is where it's not bypassing the authentication, the normal authentication. This is where if you know about special commands on the system, you can just execute those commands without being authenticated. And so one popular thing that's in a lot of web applications we found was the idea of invisible parameters. So parameters that are on the GET or POST, but they're not in any form field. They're not on any web page. So the application is processing them, but you would have had to know about them. And the only way to know about them would be to statically audit the code, pretty much. Undocumented commands are popular. You just add new commands to the normal command parsing. Leftover debug code, whether it's intentional or not, is a potential backdoor. And we actually found in this category that sometimes this was combined with special IP ranges, so that the backdoor couldn't be used by anybody, could only be used by someone from a particular IP range. That looks suspiciously like something a manufacturer would do. So first category, first example of this goes way back to '94. I think this one was found in just a few days, but someone manipulated the IRC2 client to add a couple of commands, jupe and grok. And if you issued these commands, what it allowed you to do is execute shell command on someone you're talking to over IRC. So someone on your channel, you can execute a command on their machine. It was pretty simply put in, and it was pretty simply detected. But again, this is an open source program. If this was done in a binary program, it'd probably be much harder to detect. WordPress is a web application which was recently found to have a hidden functionality put into it that basically was equivalent to remote command injection. This was the download servers were compromised in this case, and I think it was detected in about a week. Yeah, in 1 week. And here's the code that was inserted in there. You could see that there's this getIX parameter. So there's this invisible parameter that they insert handling for. So if you put this parameter IX equals some piece of PHP code, then this backdoor will execute that PHP code. The other hidden parameter they put in was IZ, and if you knew that was there and you put IZ equals a system command, it would call this pass-through function and it would execute that command on the system. So this seems to be a pretty popular. We found a few instances of this type of web application backdoor. The Artemetic CMS looks very suspiciously familiar to that the WordPress backdoor, except they went one level further here and they attempted to use obfuscation. So they bought them another week. This one took 2 weeks to catch. So you can see here that in the code they set a value to this long string, and then they put it through base64 decode, and then eval will evaluate that PHP. So if you decode it, you'll see that they have added 3 invisible parameters to the URL, include, which then will go and include a PHP file. CMD will then execute a system command, and PHP will do an eval. So they have 3 ways of basically injecting code into the system. Okay, so now over to a binary one. This is the Quake server. In 1998, was discovered to have a Archon command that could be sent to it with the special password TMS, and would execute a system command on the system running Quake server. The packet source address had to be a particular subnet, and it turned out that this subnet was the subnet owned by id Software, which makes the Quake server. So this is obviously a manufacturer backdoor. But it was also a big vulnerability because it turned out that the commands came over UDP, so it was possible to just spoof that source address easily, and then anyone could take over. And so this lasted for several years through Quake 1, Quake World, and Quake 2. If anyone discovered that, they obviously had a nice hole for a long time. TCP wrappers in 1999 had a backdoor put into it. This one only lasted 12 hours. So again, you can see that the pattern here is binary lasts years, so open source lasts only a few hours. I think that is a testament that open source is better protected from backdoors, or maybe we just need better binary analysis. But you can see in this one here, if the client connected to port 421, it exec a shell, a privileged shell, for the user to connect to. And then finally, another web application which was another invisible parameter. This one wasn't very well obfuscated, as you can see here, that the name of the parameter was backdoor. So maybe grepping your code for backdoor would be a really simple way to find them. But I don't know how long this one lasted. It probably didn't last very long. I didn't attempt to hide it at all. So detection here, common pattern is in scripting languages, because it's a scripting language, so everyone can read the code, is to obfuscate. We saw it commonly with base64, but there was other encodings, and sometimes they would do multiple encodings. But of course, you can just unwind it. And whenever you find something that's going into base64 decode, and you're doing an audit, you're going to want to deobfuscate that and inspect it, because it's probably pretty suspicious. So here there's a string. You can actually do a Google code search for this, for looking for eval of a base64 decode, and you come up with a lot of things. So that's a simple detection mechanism. Another one is to look at the get and post parameter processing in the application. So let's look at all the parameters that are getting processed by the application and enumerate all those, and then go and look and see if those parameters are used in the HTML or the JSP. Because if those parameters are never sent to the client, then there's no way that the client could legitimately send them. So it's something that's hidden functionality. The other one to look for is just look for regular old command injection. That seems to be the most popular kind of hidden functionality. So if you have a way to scan for command injection by looking for all those ways to send a system command, and then following the data flow back and see if it's tainted coming from the user, that will find this type of backdoor. And then another one, which could be a lot of false positives, but still very worthwhile, is to find the application commands in the application and audit those commands to make sure there's no extra commands in there. And then finally, if there's any kind of baked-in static IP address or host name, that's pretty suspicious. Now, of course, the manufacturer, might legitimately do, updates of content or something like that, but you want to definitely audit that code. That's pretty suspicious. So for the next two categories, I'm going to turn it over to Chris Eng.
Okay, so our third category is unintended network activity, and this is kind of an out-of-band communication by the application. So the other two categories we've talked about are usernames and passwords, but coming over the standard interface. Same for the hidden functionality. You're still coming over the same interface as the regular application. You're just accessing some otherwise hidden stuff. In this case, with the unintended network functionality, it can take a few different forms. You've got the application possibly listening on an undocumented port. This is one of those things that's actually pretty easy to find through dynamic analysis. Just looking to see where the application is actually listening with a netstat or something along those lines. Also, any application that makes an outbound connection. It could possibly be leaking information over the network, secret information, otherwise sensitive information, and exfiltrating that information via any number of common protocols. SMTP is something that we've seen, but you could easily create a covert channel through UDP or ICMP, and there are all sorts of talks on how to do that with the various option fields and things that are in the network inside the packet headers. Also, any sort of unintended network activity can be combined with rootkit behavior to actually hide that activity. So we're going to talk a little bit about the rootkit stuff later, but probably not go too deep on that because that's an entire research area in and of itself. So here's some examples. Back in 2002, there were actually a few programs, very popular open source programs, that were backdoored kind of in the same fashion. In this case, OpenSSH, several versions in 3.2 and the 3.4 series, the source distribution was backdoored, and so it would actually install itself as part of the build process. So what happens is somebody added a file called bftest and basically it looked like a test case for Blowfish. It was, in fact, I think I have it. So it had, this chunk of, data that they say is ECB data, and it just prints out some messages that say that it's testing. But then at the very bottom, you can see it goes through a loop over that array of data, and it XORs it with, a constant 47, and writes that out to standard error. And actually, it's actually a program that then compiles, and that actually runs. That becomes the backdoor. The whole file isn't shown here, but that's, you can see how it was kind of masquerading as an actual test program. So when that actually happens, it would generate that shell script that creates a file called conftest.c. And when that was built and run, it would create a command and control channel and connect outbound to a remote hard-coded server on port 6667, which is normally used for IRC, and which a lot of places actually allow outbound connections for, which is probably why that was chosen. And it sits there and listens for a command. It takes one of 3 commands, either kills itself, spawns a shell, or sleeps for an hour, and then just repeats that process until it dies. So this obviously gives a remote attacker on the box that this thing is connecting to the ability to run any command on this box. So this was detected very quickly, and 2 days. Again, open source being pretty quick. And in this case, it's the delivery mechanism that was the application. OpenSSH distribution itself was the delivery mechanism, but really, this thing takes more of the form of a system backdoor, because it was running on its own, independent of OpenSSH. You didn't have to have the SSHD daemon running. This just installed itself as part of the build process. TCP dump and libpcap were also backdoored in almost exactly the same way and exactly the same time. Somebody obviously picked some very appealing targets. But basically the mechanism was the same. The configure script was modified, it downloaded this Trojan file, compiled this command and control thing, connected to a different port, but essentially the commands were the same, the behavior was exactly the same. The difference in this case was that TCP dump itself was also modified to filter out traffic on that channel. So if for some reason you were looking for any traffic on that port, it would just, it wouldn't show you. I've got an example of that piece of code. This is the part of the code in TCP dump that deals with user-supplied filters. So like with most sniffers, you can provide a filter on the traffic so that your whole screen isn't scrolling with every single thing that's going on the network. So you can say, I only want to see traffic on port 80, or to a certain host. So in this case, it's parsing that user-supplied filter and saying, if the user specifies, if 1963, which is the port it used, is anywhere in that user-supplied filter, then replace it with port 1964. The user would never see this, but TCP dump would only sniff on that port instead. And otherwise, it would just append if there was, if the user supplied some, some long filter, it would basically just append, or I guess prepend, not port 1963 to the front of it, so that regardless of what they were doing, none of the traffic from this backdoor would show up. So this was kind of in combination with the original backdoor to just kind of make it a little bit less detectable. Obviously, if you're sitting upstream from that, you could see all the traffic, and if you had a router or any other box on the network, you could clearly see the traffic. But not everyone's always looking for that. So here's an example of a PHP web application that had unintended network activity. And this was Edomite CMS, I guess just a content management system. And it was modified to allow remote command injection, one of the mechanisms that Chris had talked about before. The difference with this one is that it also sent a beacon email out to a hard-coded email address, basically telling probably the person who inserted the backdoor that, look, here's a compromised instance that you might want to connect to and execute commands on. Here's what it looked like. Again, we see this the eval base64 decode idiom, which decodes to what you see below there. So you see the hidden parameter CIJ, which actually does the command execution. On the bottom there, you see the call to the PHP mail function, and there's the person's email address, or probably anonymous remailer or something like that, that sends the server name and something just masquerading as an error message to this email address. So now he knows exactly where to go to, exactly who's installed this, and he can go and execute commands on that server. So from a detection standpoint, identifying outbound connections is a good start. You've got pretty well-known API functions, regardless of the language. You've got standard, connect, send to, things like that. They're the standard C APIs, and you've got Win32 API equivalents. And no matter what language you're programming in, you've got certain API functions that are going to be used to establish any network connectivity. You want to focus on any outbound connections to hard-coded IP addresses or ports, obviously. That's going to be kind of an indication that something is out of the ordinary. You may have to trace back, from the send calls, and you look at the parameter that's being that contains the data buffer, trace back to see what that contains, to see if it's actually sending out any potentially sensitive information. Also look in scripting languages like PHP. In the previous example that we just saw, there are going to be special function calls to implement protocols like SMTP, and it's got the mail function for that. So while you could open up a raw connection to port 25 and actually speak the whole SMTP protocol, they try to abstract it one layer further and just provide all that functionality via functions like mail. So you need to look for those as well. Keep in mind when looking at outbound connections that the auto update features of many programs will periodically connect back, check for updates. So that could be a false positive. So you have to keep that sort of legitimate network connections in mind when you're doing some of these things. Some apps also phone home for license enforcement and things of that nature. Some people would call that a backdoor, but that's up to your discretion. Potential leaks of sensitive information. One good way that we've thought of to do this is to look. So a lot of times sensitive information is encrypted or decrypted from somewhere. So you can kind of start with any calls to known crypto API functions. Again, this is a known quantity. You've got standard APIs that people tend to use. You can start with OpenSSL, MS Crypto API, BSafe, whatever API, and enumerate all those calls. Then narrow down all the functions that handle any sensitive data. So you know which functions to look at and which parameters in those functions to look at. And then you can trace those variables to see where else they're used, where else they're referenced. If the same variable is referenced in an encryption routine as the data buffer, and then is then referenced later, sending out over TCP to some IP address, you can make the connection and say, oh, this piece of sensitive data is being used in multiple places in something that doesn't look like an approved function. Now, kind of an approved function would be other crypto API calls. So you might encrypt something and decrypt it, or you might zero out a buffer or check the length of some buffer. You're going to find references to these variables, and you have to kind of filter out those valid references and to find the ones that you're actually interested in. Unauthorized listeners, again, standard API calls it's pretty straightforward. You know how a program is going to bind to a port and accept connections or listen for inbound traffic. And finally, you can profile binaries by looking at the import tables. anomalies in just application behavior are a thing to look for here. Say I've got a desktop-only application. I downloaded like a Paint application or something, and I look at the import table using one of these standard tools, and I see that it's using all these network APIs. Well, that might ring a bell, an alarm bell in my head, saying, why is this desktop application, this console application, making all these these outbound connections? Or why is my Paint program using encryption? So that can be one way to, at a very high level, pick out some unwanted activity from a binary perspective. And then you've got to dig in a little bit deeper with IDA Pro or your favorite disassembler and actually figure out how what the code paths were to actually reach those points where those calls were used. So our fourth major category is manipulation of security critical parameters. And the idea with this category is there are going to be certain variables or parameters in a program that have security implications. They're going to be more sensitive or more critical than others from a security perspective. Any unauthorized manipulation of those values could signify that there's a backdoor present. And an operating system, which like I said before, is kind of the holy grail of backdoors. Security critical parameters in kernel code might include privilege levels of the user or the process, protection bits, even scheduling priorities. And you could have a backdoor to launch a process a certain way, and then suddenly it automatically gets gets priority over the other running process. Anything that gives that process some sort of advantage that it shouldn't otherwise have. In higher level application code, if you think of web applications or any desktop application, authentication functions, authorization functions would be the prime location of any security critical variables, parameters. So we talked about this, alluded to this before. In 2003, there was an attempt to insert a backdoor into the Linux kernel. And this didn't actually make it to a shipping kernel. It was detected before that, thankfully. But here's the code that accomplished this particular backdoor. It was in the syswait4 function in exit.c. in the kernel, and wait4 just tells a process to basically wait for its child processes to terminate before proceeding. So here was the piece of code that was inserted, and it checked the options, and it said if the options that were passed into this function had these two flags set. And the current UID was 0, meaning it was running as root, then return this particular return code. Well, if you look a little bit more closely, what actually is going on here is that it wasn't doing a comparison to see if the UID was 0. It was actually assigning the UID to 0. So you've got an assignment instead of compare, which if you're not watching closely, it's a common programming mistake. Unlikely common programming mistake to happen in this piece of critical code, which is why it kind of, I think the person who wrote it tried to sneak it under the radar. You could tell that it was somebody that was fairly familiar with how the Linux kernel works, because basically you would never pass that combination of flags, wclone and wall. They're redundant. They're overlapping basically. Wall includes wclone. So you would have to. There's no chance that somebody would accidentally call the wait function in this way. So it was very, very sophisticated. Actually, one other thing to mention about this one is that probably the only reason it was detected was the mechanism by which the person tried to insert it. They actually directly manipulated the files in the CVS tree. They didn't actually make a valid commit to the tree. They actually went to where the CVS root was and modified those files, and then I guess whoever came in after them tried to check something in or do an update or some other actual CVS operation, got some sort of weird error or some indication that files were out of sync or something like that. If it had just been a normal check-in, I don't know, there could there could still be a backdoor in the kernel today, because somebody might not have actually seen that anomaly in the CVS. Here's another one in the X server, and this one, I'll start by saying that this probably was an implementation error, because again, it's another one of those common types of mistakes. But there's really no way to be certain that it was implementation error. But this is a pattern that a manipulation of security critical parameter could take. In this case, with the X server, there are some server options that were designed to be restricted to root. So only root could say, set my module load path to this particular location, or use this configure option, which presumably does something useful. If you look at these two sections, focus on the top section, where we're setting the module path where we can, where the X server is going to load modules from. And you can see in the first conditional, it's going to say that if the user ID is 0 or root, or get EUID, which is get the effective user ID, what the process is running as, is not root, then go ahead through and allow them to process this module path option. The bug here is in the conditional itself. If you see the first part of the conditional calls the get UID function and compares it to 0, whereas the second part of the conditional compares the get EUID function pointer to 0. There's no parentheses, so it's not actually calling the function. Unless basically get EUID's memory address, where it's located, that function is located in memory, is always going to be non-zero, and that part of the conditional is always going to evaluate to true. So the arbitrary loading of modules is going to that conditional just basically becomes ineffective. The bottom one suffers from the same symptom. They're doing they're not calling the function, they're just comparing the function pointer to 0, and it's never going to be 0. So detection, this can be very application specific. Other than operating system code, where you kind of you know that there are going to be certain things that are security critical, like the UIDs that we talked about before in the Linux kernel. In an application, you kind of have to have a little bit of design information to understand, what are those variables called that store the current user ID or the current logged in user or any other anything that's critical to that particular application. But the mechanisms by which those are altered or manipulated are kind of the same. You can still look for assigns instead of compares in any piece of code. You can also look for a conditional where there's an assignment. The right-hand side is not the return value of a function. It's pretty common in C to allow in a conditional to actually put a function call in there, and then if the function call succeeds, then that evaluates to true. But if you find cases where the right-hand side of that conditional is not actually a function, or it's a function that always returns the same value, that could be that's obviously code that's not going to be doing what it looks like. Logic expressions in any security critical code that that are kind of botched, like a short-circuited expression. There's an example there. If true or is authenticated. Now somebody's not going to put true, but they might put something that always evaluates to true, kind of like the function pointer comparison. So any sort of logic expression that gets short-circuited it could be potentially suspicious. Here's some things that kind of didn't fall into those other categories, but some other things to look for. They could span really any of the categories. Embedded shell commands is just something that you always want to look for because it's very easy to just search for particular strings. Time bombs, things that set up particular time windows of opportunity to allow certain functionality to be switched on or off selectively. Rootkit-like behavior, kind of alluded to that before with the hiding of the network functionality. And then some other code or data anomalies that I'll talk about. So low-hanging fruit, grepping through source, running for strings and binaries, looking for bin sh bin bash, bin cache, all the standard ways to just execute a command. Sounds silly, but easy enough to do, and for the time it takes you, you can find something useful through that grep. Obfuscation of static strings, people trying to hide their tracks a little bit, but not understanding that things like base64 and UU encode and ROT13 and XOR are trivially reversible. Any sort of file system usage that looks abnormal, putting a lot of temp files, using alternate data streams in Windows. Who uses that? But it's still there. So if anybody's doing that, that could be that's a common way to hide stuff. Date and time library calls, again, going back to the API, looking for those date and time calls that might be used to determine, during runtime if it's a certain date, or if it's, maybe you've got that hidden parameter in the web application, but it only activates if it's the first Wednesday of the month between 12 and 1 a.m. So it's got to figure out that stuff somehow. So you can look for those standard calls to time functions. False positives in detecting these are going to fall into the logging category. A lot of programs, when they create log files, need to get the time to put in the file. Execution time calculations that people leave in there for just for QA purposes are going to do some calculations on the current time, before and after an operation, for example. Protocol timestamps. If it's implementing custom protocol and it's got to put the current time in a field or something, you're going to see those calls. So there's potential for a lot of false positives here. Rootkit-like behavior. I won't go over these in a lot of detail, but basically looking for some of these things that are indicative of process hiding or Win32 hooks, DLL injecting code into another process, keystroke logging. And again, these are often implemented through very specific Windows calls. On the Unix side, in Linux, there's some ways that you can write in code to do hooks and a net filter, custom protocol handlers that might be in there to look for, say, a magic packet or something like that. So this is another whole research area. Rootkit.com's got a lot of good techniques for this stuff. I would say that the false positives here are probably going to fall into the category of if the application that you're looking at is, let's say, a debugger, well, then it's going to have to attach to processes and query the memory pages and do some of these things. But I don't think that there are a lot of programs that legitimately would need to call these functions. So so the presence of some of these can be an indicator that something is trying to be hidden. And finally, the code and data anomalies. Any self-modifying code, the PHP examples that do the eval and rewrite themselves, or the OpenSSH example where you had the block of ECB that XOR'd itself and then dumped out to a file. Anytime the program manually writes into a code page or jumps into a data page, I mean, that's not normal. And that falls into the self-modifying code category. Also unreachable code. If I, as a developer, check something into a repository and let's say I just check in a function and nobody calls it, well, technically it's not a threat at that particular point, but what somebody could be trying to do is kind of a multi-stage insertion. So first they check in something that does something malicious, but never gets called from anywhere. So it could be masquerading as a kind of a piece of debugging functionality. So the person reviewing the check-in says, "Oh, that's just for debugging. It's not, nobody's calling it. It's just in there. Somebody will turn it on later if they need it, that sort of thing." But when what somebody could do next is in a completely separate check-in. Maybe they wait 6 months later. Maybe they wait a year, and then they just insert something else that calls the debug function. Somebody else is reviewing that check-in, or maybe it's the same person, but they don't remember it. But the fact that you're reviewing these little pieces at a time may allow the person inserting the backdoor to get past some of these code auditing mechanisms. So watch out for unreachable code. Okay. Backdoors and malware. Kind of an interesting idea, I suppose. Any application can really contain a backdoor, even things that are advertised themselves to be backdoors. So you may install, Sub 7 or this Optics Pro backdoor on your system, and you configure it with a password so that you can access it remotely. Some people use these, back when they came out, just as remote control mechanisms for kind of utility. So it's kind of like an alternative to a remote desktop or something. You just install this, and now you go somewhere else, and you can connect back to your computer, and you've set it with a particular password so that only you can get in. Well, it turned out that in both of these cases, with these very popular backdoor packages, that the authors had embedded master passwords. So they made sure that they could always get in to these things once people had installed them. In the first case, the Optics Pro case, once it was kind of detected and somebody said, "Hey, what's this?" they claimed that it was a security measure to reduce the popularity of the application, so that I guess if the FBI started coming after him, he could release this master password to the world, and suddenly everyone would hear about it, and then the people running it would basically take it down or not want to use it anymore, and therefore the overall impact of the footprint of this thing would decrease, and the FBI wouldn't care anymore. I don't know. It doesn't sound like a very likely story. But he did acknowledge that there was a master password there. Same for Sub 7. It's just again, it's just a long string, just embedded in the application that after it compared against the configured password, compared against the master password, and if that was provided, then just let the guy in. And here's the disturbing one: exploitable vulnerabilities. If you want to put a backdoor in a program, you could do any of these other things that we've talked about. You could, you could put a hidden parameter in there. You could make it call out. You could, manipulate parameters, whatever. What if you just embedded a vulnerability? What if you just, wrote a function that had a Stack Overflow in it? Well, I mean, technically, if you make it easy enough to exploit, if you lay out the stack properly, or you put it in a location that's called from the right places, and you can make vulnerabilities more or less exploitable depending on where they are and how they're called. You could write your input validation, your security, your actual security function, your input validation. You could write a regex that isn't quite correct. Regex are really complicated. It could be something that looks good enough for the auditor to get past code review, but in certain circumstances you can fool it. They're so complicated that that sort of thing would be likely to get through. So this kind of the idea of a vulnerability as a backdoor is kind of blurs the whole definition of what constitutes a backdoor. And what it does is it may not be as straightforward to exploit, but it gives the person who did it a level of plausible deniability. If somebody comes to me after I put this Stack Overflow in that could be it's integer overflow or whatever, and they say, look, somebody could take over the system with this, I can just say, oh, I didn't know I shouldn't use getS, and it basically just looks like a developer mistake. Now you can only do that a few times before you get fired for in confidence, but you can see it's not quite as cut and dry as, oh, there's this parameter that calls system. You can't really prove that I intended to put the vulnerability in. So technically, any vulnerability that's ever been discovered in a piece of code could have been a backdoor, but So, what time is it? 5:45. Okay. So one thing that we did as part of this was just to write a quick proof of concept of the idea of using static analysis in an automated fashion to detect certain patterns. So we wrote in IDA a script for one of these categories, and what it basically does. It was one of the ones that Chris talked about in his section, which was looking for static strings being passed into crypto functions, and that's what was used in the Borland interbase backdoor. So what we can do is we can start with all known crypto APIs, look for calls to that, look at the parameter that we know is the sensitive one, and then trace that back using IDA to figure out if it's a static string or not. So let me pull up something real quick here. What we basically did for the purposes of this is that we just took some open source FTP program and inserted a backdoor in that. So let me clarify, pure FTPD does not have a backdoor in it. We put this in for the purposes of this. I'm going to pull up this file. Actually, let me talk about the script first. It's loud. So what the script basically does is, like I said, it looks for all instances of a set of crypto functions, and those are basically kept in a data file. So it's pretty straightforward. It's just by name. So the first word is the function name, and then the number out to the side of it is which parameter we're looking to see if it's a static, a constant string. So if the first parameter to crypt is constant, then flag that, and so on. You can see that all the OpenSSL API functions are here, and a couple other APIs. Here's some Win32 specific stuff. Obviously, this can be very easily extended, especially if you've got your own custom APIs that you're using. So this is the data file that the script uses. And basically, what we do is just open up your binary in IDA. Okay, and then you load up your script. It asks me where the file is with all the functions that I care about. Pick that. And then you see down here, basically it just says here are all the addresses where a constant was pushed to the function. And there's where all the function calls are. So I can double click on each one of these to be taken to where that happens in the code. I don't like this mode for this. Put it back in text view. So here I can see that a constant was pushed into EAX, and then it was put at ESP+4, and then crypt was called. So there's this weird string here, with a bunch of numbers and dollar signs in it. So I'll look at each one of these. Okay, in this case, it's passing in something similar. More stuff that says test, calling crypt on that. This last case, here's our backdoor. I'll pull up the source to show you this in a minute, but this one, you can see it's passing in BH 2007 as the first parameter, and XZ is the second parameter, which is just the salts. It doesn't matter. And then it's calling crypt. So that's all four of these at the moment look suspicious because we don't know what those first ones are. But now we can pull up the code and actually take a look at it. So in this case, we took the same approach as the Borland guys and just said, basically, this is the function that parses through. There's a password file. So pure FTPD has the notion of virtual users. So like I'm running the server on Windows, I don't need to have every FTP user mapped to an actual system user. I can create basically a password file that has virtual users, and then once I have that password file in place, I have to run this executable pure PW with a make database command, and then that takes the password file and creates the actual password database that pure FTPD uses. So this is the function that parses that file and creates that database. And you see there's a loop that goes through all those, And then at the very end, it calls crypt on our BH 2007 password. It does a sprintf, which is, this is, you can kind of see this is password file syntax, and then it calls the function that adds that set of credentials to the database. So no matter what you do, when you call this make database functionality, it's going to stick this one at the end. So you can see how that was pretty easy to detect just based on known API calls. That could have been any that could have been des encrypt or any sort of function. As long as we're looking at the right parameter, we'll find those uses. If we want to look at the other ones, basically the other ones actually are tests. They are in there. It's just basically does a crypt, and it compares the output of the crypt function to what it expects the output of the crypt function to be. So I won't really dwell on those. But you can see how this would be pretty easily extensible to some of the other detection mechanisms that we talked about, simply because a lot of them do focus on known APIs. And you're going to be looking for different things in each case, but basically, the scripting mechanisms of IDA allow you to kind of write that sort of functionality and just look for those sort of suspicious things. Let me try and figure out where we were here, and then hand this back over. All right.
So just some final concluding thoughts about what we found with our backdoor research of how these things played out. Backdoors are, if you're an ISV and backdoor is found in your code, it's typically worse than a vulnerability being found in your code because they're typically trivially exploitable. So you're not going to have to write a tool to exploit it. You can usually do it at the command line or through the web browser. So they're always going to have a high severity because of that. The other factor is if a backdoor is detected in your code, the press treats you very differently than if a vulnerability was found in your code. If a vulnerability is found, it's, your developers need training or you're just not so good at coding. But if a backdoor is found in your code, it looks like you're basically incompetent. You don't have control over your development process or your distribution points. So for those two reasons, auditing for backdoors is something which is probably more important than just auditing for regular vulnerabilities. So if you're an ISV, or you're on an open source project, it probably makes a lot of sense to audit with this along with your vulnerabilities. So when you're going to look for it, it's probably a good idea to scan your code before you release it. Another case is when you're doing. Most people don't write 100% of their application. They link to libraries, whether they're shared or static, different application frameworks, different vendor libraries, database libraries, graphics libraries. So those could contain backdoors in them also. And that's a case where you're sort of acceptance testing binary code when you decide to use another party's package and make it part of your application. So this is a place where you're going to have to do it at a binary level. And then just a final thought. There actually is another way that it can be a backdoor can be inserted. It's not necessarily a distribution point of the code. It could be your compiler or your linker has been backdoored, and so the tools you use to turn the source code into the binary could actually be inserting the backdoor. And this is something that Ken Thompson wrote a paper on, Reflections on Trusting Trust, where he actually did this. To the Unix operating system, sort of as a proof of concept, he backdoored the compiler. So whenever it compiled the login-C program, it put in a special credential in there, so he could always log in. And at the time, binary analysis was really not conducted. There weren't good tools to do it, and he kind of posits in this paper that we can't really trust any code because the the tool chain could be compromised. So how would we ever detect the backdoors? But now here we are in 2007, and there's a lot of good binary analysis tools out there, and so it would be possible to find some of these backdoors today. So that was all we had for our presentation. I guess we have a few minutes if there's any questions. Steve?
Someone could clearly implement the APIs and call directly the kernel system calls and so on. Do you have protections for that?
Call the kernel system calls? So like instead of calling...
API entirely set up their own code to make system calls.
We haven't implemented those, but that's something that you certainly could do.
Watch for, you still have to watch for like certain sequences of functions, right? Certain, a particular higher level API call is still going to be implemented a certain way underneath. So, you could watch for a particular sequence of events and do it that way. There's no reason why that couldn't be done.
All right, well, thank you for coming.